Okay, folks, so we've just solved the three-dimensional particle in a box problem, and we found the wave functions and the energy levels. I'd like to take a closer look at these. So first, let's take a look at the wave functions. I'll show you some plots, and then we'll take a look at the energies. Actually, the energies are going to turn out to be sort of more important to us, and also, in some ways, easier to comprehend. Anyway, let's take a look. Hold on, I want to share my screen. Okay. Here I'm showing a graph of the wave function for the two-dimensional particle in the box, because the three-dimensional one is sort of beyond the capabilities of my system, of my screen here. Okay, and right now we're looking at the nx equals 1 and y equals 1 wave function. In fact, if you look at the function we're plotting here, you can see that nx is being represented by n, and ny is being represented by m, and then I've set L equals to 1. Oh my gosh. Okay. Let's see if I can get this to look a little less ridiculous here, so we can take a look at some of the others. Now let's see if I can get it to spin a little bit. Oh, it doesn't really want to do what I want. Okay, well, let's see what we can do. In any event, let's take a look at another wave function now. How about nx equals 1 and y equals 2? There it is. There we are. Oh my gosh. I apologize for, there we are. Okay. How about nx and ny equals 2? Okay. So now you can see we have one complete cycle of oscillation in the x direction, one complete cycle in the y direction, and notice that the wave function goes to 0 at all of the boundaries. Okay. We can have higher order ones too. How about ny equals 4 and nx equals 2? Oh my goodness. A little difficult to get this to do what I want. I think there we go. Or 3, or 4, or 5. Okay. And there we are back at the first one. So that's what the wave functions for a two-dimensional particle in a box look like. And you just have to use your imagination for the three-dimensional system. Very good. Now, if you have some patience, let's look at the probability densities. Excuse me. There we go. We just have to square the wave function. Let me rescale this. There. Okay. It looks a little subtly different, right? Now let's look at one of the higher ones. Nx equals 2. Oops. There we go. How about nx equals 3? Or I seem to have lost control of the m parameter here, so I'll just type it in. How about nx equals 4 and m, or ny, equals 3? Okay. You can see that we, of course, all the peaks are positive now. And in between the peaks, we have nodal lines instead of nodal points. There we go. Very nice. All right. Anyway, I wanted to show you the probability density for this two-dimensional particle in a box. Oh, one other thing. So here we have nx equals 1 and y equals 2. Have you wondered why we can't have, say, nx equals 1 and y equals 0? Here, let's try it. You'll see immediately. Of course, if ny is equal to 0, then in the second term here, we have sine of 0, which is 0. And so that gives us a wave function which is 0 everywhere. And that corresponds to not having any particle at all. So it's solution, I suppose, but a not a trivial one that we're not interested in. That's why any system that represents a particle in the box has to have a non-zero integer for each of the quantum numbers. All right, now let's stop here. Okay, lastly, let's look at the energy levels for the 3D particle in a box. Okay, 1 second. All right. So of course, the important thing here is that we now have 3 quantum numbers, nx, ny, and nz, okay? And so we have more possibilities in our system. Suppose each of these is 1. This represents the lowest energy state of our system. Then the sum of the squares of these which is what enters into the energy formula. What's that? Well, of course, it's just 3, right? And so then we can figure out the energy here. And the energy will be 3 times, let's call it 3 times E naught, where E naught will be, in this case, H squared divided by 8m L squared. Okay? So now we've written down the energy of the lowest state for a particle in a 3-dimensional box. And look, it's 3 times higher than it would be for a 1-dimensional particle in the box of the same length. Well, let's look at some of the other states now. How about the state 1, 1, 2? What's the energy here? Did you figure it out? So now we have 1 squared plus 1 squared plus 2 squared is 6. And so the energy is 6 E naught. But notice, this isn't the only way to get that energy. There are 2 other states that are very similar. The one with ny equals 2 and the one with nx equals 2. And each of these have the same energy of 6 E naught. Okay? These are called degenerate states. Now there are 3 quantum states that have the same energy. This is common in 3-dimensional systems, degeneracy that is, but it doesn't occur in 1-dimensional systems. So it's something new. Okay? Okay, here's another block of states. How about 1, 2, 2? So the energy for this one, well, 2 squared is 4, so 4 plus 4 plus 1, that's 9 E0. Okay? And in this case also, there are 3 states with the same energy, or 3 degenerate states. Okay? Here's another state, 3, 1, 1. What's the energy of that? Okay, I'm sure you figured out it's 11 E0. Okay? And how about this state? Oh, I'm sorry. The 3, 1, 1 state is also degenerate. And here's one more I'd like to look at. How about 2, 2, 2? What's the energy of that state? Well, it's clearly 3 times 4, or 12. So Let's make a sketch of this in a second, but before we do, let's take a look at something. Notice the lowest state is non-degenerate. There's only one state at that energy. Then we have a triplet of states, another triplet of states, a third triplet of states, and then another singlet, okay? The states at first might appear to be equally spaced in energy. Energy of 3E0, 6E0, 9E0, and so on. But when we get to the 3-1-1 state, it breaks the pattern, okay? Finally, we can make a sketch of these results. Oops. There we are. Okay, the lowest state has energy 3E0, and then the next state has energy 6E0, 9, and then 11 and 12. So I'm just highlighting that these are not really equally spaced. As we get higher in energy, they actually get closer together. Okay, let's stop here with this example. Okay, so the fundamental thing about particle in a three-dimensional box, a couple of things to notice. First of all, there are 3 quantum numbers now. 3 dimensions, 3 quantum numbers. In addition, our wave function now extends over 3-dimensional space. In a 3-dimensional system, or at least in this one, we have the possibility of degenerate states, more than one state at the same energy. This is common in highly symmetric problems like this one. The hydrogen atom is another highly symmetric, spherically symmetric problem, and we'll see that there are degenerate states there. All right, well, let's stop this example and go on to the next one.